Hello, this is Ian Vogelesang, and this is the Demo 1 Fixed RAID video. Okay, let's go to the demo output. Let's click on Demo 1 Fixed RAID, and then we can see that we've got a folder for the subsystem configuration showing that we have a command device. We can see the same roll-up as we saw before. We can see the same step folders that we saw before with DF. Let's take a look at the IvyScript program. In the IvyScript program, because I have 4 LUNs which are showing up on both ports 3C and 4C, what I'm doing in this case is I'm creating a workload called steady on each of LDEVs 0 and 1, the instance that shows up on port 3C. And then separately, I'm creating a workload of the same name, but on LDEVs 2 and 3 as visible on port 4C. And here I haven't specified any parameters because I'm going to set them once for all workload instances here with the edit rollup all equals all, and I'm setting them to IOPS max, 100% reads, max tags equals 32. And then the rest of the program is the same as we saw with DF. So let's look at one of the step folders, and you can see that inside the step folder there's a subsystem performance data folder in addition to the folders for each of the rollup types. So let's look at the RMLive API performance folder. You can see that there are different types of resources for which we get RMLive API performance data. At this time I collect most of the data, but there's still other resource types within the subsystem for which I haven't provided support yet. So over time I'll be fleshing this out to cover all RMLive API types of data. And then if we look inside any one of these, you can see that there's a CSV file for each of the instances of that resource type. In this case, we can see that there are 3 clippers, and if we look at any one of these clippers, then you'll get one line at t equals 0. So this is the gather that happens before the first subinterval starts. And then there's a gather at the end of each subinterval. So we have subintervals 0, 1, 2, and 3, and we can see the data that's being gathered there. Here we can see write pending megabytes as well as write pending percent. If you take the write pending megabytes and you divide by the cache size in megabytes, then you'll get a very high resolution write pending number. Okay, let's back up here, and just to reiterate, for LDEVs you get data for every LDEV in the subsystem, whether or not it's involved in the test. Okay, so having looked at that, let's look at the overall test result and look at the all equals all CSV file. And now you can see that compared to the DF CSV files, when there's a command device, you get extra columns that are appearing. And in these extra columns, you can see the drive type, you can see the drive quantity, you can see the RAID level, parity group, layout, etc. Then you can see a set of columns here which appear when you have a command device. You can see the subsystem MP core count. You can see the subsystem average MP core busy percent. The clipper count is the count of the clippers that are reporting in this test. The subsystem MP core count is the number of cores behind the specific LDEVs that are under test. This is a read test, so the average write pending is 0 all of the time. We can see the number of parity groups under test. We can see the percentage busy of those parity groups. We can see the number of LDEVs under test. And then here, I find these very useful. You can see the host IOPS per drive. So this means per FMD, we're starting out at about 33,000 host random reads. And then when you get the block size all the way up to, what was it, 16 mega, or it was a big, what was the block size? 1 megabyte. You can see the megabytes per second. You can see the application level service time, Little's Law, queue depth per drive. So we can see in this test that we're getting a queue depth of about 16 per FMD. When you multiply by the 8 FMDs that we're testing, you get the total queue depth overall, which you can see over here, which is 127 or 128. Then here's two key columns to validate that your device driver isn't doing anything funny. We can see what the subsystem reported IOPS is as a percentage of what the workload threads on the hosts reported. And in this case, it looks healthy because, and you can see there's a slight disparity, but you can see that it's a one-for-one relationship between the number of IOs that the host says it's running and the number of IOs that the subsystem says it's getting. But if you're testing with very large blocks and your device driver max transfer size is set to smaller than the size of the block that you're trying to read or write, you'll find that the subsystem IOPS will become a multiple of the host IOPS. So this lets you right away see if there's any issues with the device driver fragmenting your blocks. Then in this column, we can see what the subsystem reported service time is as a percentage of what the host workload thread saw in terms of service time. So you can see here that for the small blocks here, 25% of the time, the application was waiting, but the subsystem wasn't even doing an I/O yet. So here what you can see, taking the difference between the service time reported by the subsystem and the service time reported by the application, you can see what I call the path latency. Okay. And by the way, right now I am counting the service time for an I/O from the moment before we issue the Linux native kernel asynchronous I/O call to start the I/O until the I/O finishes. I'm thinking of changing this to be at the from the moment that the asynchronous I/O interface returns, indicating that your I/O has been started, until the time that the I/O finishes. And the reason for this is that if there is not a tag available to drive an I/O when you issue your call from your application, then the asynchronous I/O call to start the I/O can actually block. So this includes this path latency is the time that the asynchronous I/O interface is blocking, waiting for a tag to become available in the device driver. Okay. That's what I wanted to show you for Demo 1 Fixed RAID. Thanks very much.